Hi, in this e-lecture, we're going to be focusing on processes. Okay, so this is the first step in understanding how an OS system actually works. Okay, in terms of how multiple threads can actually come together and share a single CPU and a single set of resources. Okay, so let's get started. So in this lecture, we're going to be talking about process. Okay, the memory. Okay, how we can actually switch between processes, some RTX examples, okay, process termination and context switching. Okay, so as I mentioned in the earlier lecture, okay, the whole idea of an OS is it provides a level of abstraction so that a process or multiple instances of a application can run in its own process space. Okay, so for example, I can launch multiple instances of my Kill Microvision IDE. Again, each of them have their own memory space, okay, and own process ID, okay, which will all share a common process, a common CPU, and common memory. Okay, so this is basically the objective of a OS to be able to provide such functionality, such ability for us to capitalize on. Now, when I have an instance of a program that is running, I need to make sure that that process is able to access the CPU, access the memory, and the resources in the system. Okay, so a process can have a CPU time allocation. Okay, that means in a situation where you have a round robin kind of a sequence where multiple processes are each allocated a time slice, okay, to run. I allocate some memory to the process. Okay, it could be real or virtual. Okay, which we'll come to that later. But basically, you need some amount of memory to run your application. You need a process ID. Okay, to sort of identify yourself with the OS. Okay, so the OS will recognize this process with this particular ID, and within the process, you can also have multiple threads that are running. Okay, one of the things about OS is it creates this illusion, okay, for a process that it has all the resources to itself. Okay, so it will have this idea that I have the CPU to myself, I have the memory to myself, and I have all the resources to myself. Okay, so each process sees one dedicated processor and one segment of memory. Okay, but in reality, okay, we know that the process and the memory is actually shared among multiple processors at the same time. Okay, but they can also be aware of each other. Okay, so it's still possible for multiple processors uh, to still be aware that there are other processors in the overall system, and I can have the ability to have multiple processors communicating with each other. Okay, so that is the inter-process communication. Okay, so this gives you a layout of an executing program. As you can see, basically the code that we write, okay, when we write some code, okay, it uh, will get compiled, okay, into some binary at the machine code level, and that will occupy some section of memory. Okay, and that is usually read only memory. Then you also have a lot of data. Okay, when you write a program, you may have a lot of variables, arrays, and structures, and so on. Okay, so all of them also need some memory space. Those that are initialized, okay, will occupy some memory, and uninitialized, they will go to some other memory segments. Okay, so when I say some other memory segments, it depends on another file actually known as the linker file, which sort of allocates these memory components to different addresses in the actual memory space. Okay, but we're not going to go into those details. Okay, but this is just for you to understand that when you write a program, okay, the way we declare the memory also has impact on actually where it gets stored in the actual physical memory. Okay, now another thing that we will commonly do in our program is we may want to have some dynamic allocation. Okay, so the static data is referring to data that is already known during compile time. Okay, so in the compile time, I already know I need 1 kilobyte array, I need this data structure, I need this memory segments, and so on. So those are compile time information. But while the program is running, you may want to dynamically allocate memory. So that is where the heap comes in. So the heap, you allocate a certain sort of a starting point or a pointer, and then from there, as and when you need, you grow, and then if you free up the memory, then you decrement the pointer, and so on. Okay, so there is a manner in which you allocate memory dynamically, okay, while the system is running. And of course, there's also another segment of memory which we all are quite familiar with, which is known as the stack. Okay, and that is operated through a stack pointer. Okay, so different processors may operate the stack pointer differently in terms of first in last out or last in first out. Okay, so that part is quite clear. But of course, whether you push or you decrement or increment the stack pointer, whether it goes upwards or downwards, that part depends on the actual processor's implementation. Okay, but generally stack we know is we call it the first in last out or last in first out. Okay, and the stack is used for two main things. One is of course for procedure calls and returns. Okay, whenever you jump to a function, okay, you need to save some information, you need to pass some parameters. Okay, and when you return from the function, you may need to get back some parameters or return values. So that is where the stack comes in. And of course, another important usage of stack which we saw recently is when we are having interrupts. Okay, because when you're running your main program and suddenly interrupt happens, then you need to jump to the ISR. So in order to make sure you are able to return back to the exact point, okay, so when your main program is running, okay, and then suddenly there's a ISR triggered. Okay, when I interrupt triggered, when I jump to the ISR, when I finish everything and I return, I must be able to know exactly where I left off. So that is again where the stack comes in. Okay, so I will push everything onto the stack, jump to the ISR, and then when I return, I'll pop from the stack and be able to carry on from where I left off. Okay, so this is uh, a nice summary of how data and program and the stack and heap all come together, to help us with executing our program. Now, a process, okay, is basically like you mentioned, a process thinks that it has this, or it has this illusion that it has the entire CPU to itself, okay, and the entire memory to itself, okay, in order for it to fulfill all the objectives of this process. So, and since I can have multiple processes and all these processes need to be all allocated some form of resources, some form of CPU time. Okay, when I'm switching between processes, I need to be able to keep track, okay, of what is happening. Okay, so inside the process itself, there is this information of the amount of memory that I'm using, how much, which address spaces have been allocated to me, okay, and while I'm executing the process, what is my current state, what are the values of my registers, okay, and of course the state of the OS itself, in terms of how it is allocating and managing the requirements of this process. Okay, so this is all of course at a level of abstraction. Okay, and generally when we create a process or a task, we focus on the code that we're writing. Okay, but all these are things that are related to the code that we're writing, okay, and the process in general. Okay, and of course another important thing is the terminology. In many references that you may read online or in books, they will generally use the term process and task quite interchangeably. Okay, and especially in the embedded system context, we generally like to use the term task, multitasking, in terms of multiprocessing. Okay, and within a process or within a task, you also say you can have multiple threads. Okay, so this is also another common terminology, and in some cases there can be some books or some references where they use all three interchangeably. Okay, so they may refer to as multiprocessing, multitasking, or multi-threading. Okay, but eventually the whole idea is you still come back to the basic concept that whether it's multiple threads or multiple tasks or multiple processes, you think that each of it has some objective that you want to fulfill, and you are now trying to make use of the CPU and its resources within that space, okay, to fulfill that resource. Okay, and of course there is also a lot of features and functionality in terms of uh, sharing data between different tasks and communicating between different tasks, okay, and how they can all come together and synchronize and fulfill the objective. Okay, so all these are things that we are going to be learning along the way. Okay, so all this information, like I said, okay, all this information about the process, okay, in each process in the system is stored within what we call the process control block or task control block of a system. Okay, so when you create a task, it comes together with this entire chunk or this block where all this information is there in terms of process ID, the state, the scheduling, the registers, and all this other things. Okay, so we are not going to go into everything now, but just have this idea that when I create a process, okay, it is not just the code that I'm going to write. Okay, at the OS level, I will create this process control block which creates this table of information that captures everything related to the process. Okay, and this table is updated constantly to keep track of where I'm executing, how much memory I'm using, what is my current state, what are my resources, and everything. So everything is captured within this process or task control block whenever I create a process. Okay, and this is an example of how a task control block looks like in the RTX that we are going to be using. Do not need to be overly concerned about all of this. We just need to, for now, just keep a note of these three important things: the current state, okay, the priority, and the ID. Okay, the ID is, like I said just now, is for the task to be able to be easily referenced by the OS. So the OS will sort of reference this task or this process based on the ID. Okay, so when I create this task or create this process, the OS will allocate it an ID, and it's easy for the OS to manage it through this ID. Okay, the state, we will come to that in a while. And of course, another important thing is this priority. Okay, just like interrupts. Okay, when we have interrupts, we have this concept of priority. Okay, to say who is more important. Okay, and if multiple interrupts are triggered, who should be executed first, and so on. So all those we discuss in the interrupt context. So similarly, in the OS context, when we create a task, we can also assign a priority. Okay, and through that priority, we will be able to know uh, how or what are the dynamics of this multi-threaded environment. Okay, so the priority actually plays a very important role in ensuring that the different tasks which have different responsibilities will be able to still synchronize and communicate and fulfill the objectives. Okay, so we will be having a fair amount of exercises and discussions on all of these important characteristics of a multi-threaded environment along the way. So now let's come to the first step, the process creation. When I first create the process, okay, so every OS has a mechanism, okay, some kernel call to create a process. And once I create the process, the OS will allocate the process a unique ID. Okay, so this is for the OS to reference this process or this task, in this entire array of so many processes and tasks that are running concurrently. And of course, once I allocate the process ID or the unique ID, I also need to allocate memory, okay, depending on what are the requirements when I created this task, okay. And I also need to initialize the control block and link the process control block in the queue. Okay, so this part don't need to worry so much. As long as you know that when I create a task, I'm allocating memory and I'm allocating a predefined control block, okay, depending on the requirements of this process, okay. So these are the important things that come along with the process whenever I create it. Okay, and of course I may also terminate a process. Okay, that means once the objectives have been fulfilled and I no longer need the process, I may terminate it. Okay, just like for example, you open up a Microsoft Word application, so it runs as a process, and once you're done with the Word, you just close the whole application, correct? So what happens, you release all the resources. So when you are launching the application, you acquired some resources from the CPU, and now when you release or you close or terminate the application, you are releasing those resources back to the OS. Okay, but interestingly, okay, in our embedded software or real-time environment, there is no such concept of termination. Okay, generally most of our processes never terminate, they run indefinitely. Okay, so this is again another interesting thing which we will be exploring. Okay, so just now I mentioned about the idea of switching between tasks. Okay, similar to the idea of switching from a main thread to the interrupt. Okay, so we already know this idea of context switching because when I have just a main program running, okay, and an interrupt is triggered, we know that I need to jump to ISR. Okay, so when I finish, I come back. So at this point of time, what happens is this thing called context switching. Okay, and if I don't have OS, then the context switching idea is basically a snapshot of my registers, my program counter, my status information, and so on. Then I jump to the ISR. Maybe I need to save some registers and carry on with the ISR. When I complete, I pop everything back from the stack, my program counter, my status register, everything, and I return and I carry on. Okay. In the OS context, as what I mentioned earlier, when you create a process, you are at the same time creating a process control block. And this process control block contains all the information related to the process. Okay, in terms of my register information, my program counter, my state, my priority, my memory usage, everything. So everything that is currently related to the process is always continuously updated in the process control block. Okay, which makes your life or the life of the OS very easy, because when I need to make a switch, okay, I just need to save. So it's the same idea of context switching, but now I save the entire process control block information. Okay, make sure it is updated at that current point, and then I'm able to load the process control block of the new task that I'm going to run. Okay, so the OS will always have a current process control block that is going to be used for the execution. Okay, so the process control block that the OS is going to use will have the information of the current task that is executing. So if I'm currently executing task A or process A, and at this point of time you can see that there is some event that has happened that is going to cause me to switch from A to B. What exactly is this event and why is this happening is what we will be discussing in other lectures. But for now, we just take it that at this point of time, prior to this point of time, A was executing. Okay, and at this point of time, there is something has happened, and the OS needs to switch from process A to process B. Okay, so currently the OS was holding on to the process control block of task A and making sure that was updated. But now that I need to make a context switch, it will save. Okay, so the first step is to save the state of process control B, okay, onto its own memory space, and then load the process control block of B onto its space, onto the OS space. Okay, and then I will be able to start running from process control, start running from the code in process B. So as you can see, there is some slight delay. There is some time. Okay, so this is basically the context switching time between one process and another process. Okay, so this is a very frequent operation. Okay, because in OS, multiple tasks are you can have many tasks, and many of them are trying to compete for the CPU's attention. Okay, so switching between one process and another process is something that happens very frequently, okay, in a multi-threaded environment. Okay, and it does take some time. So these are the overheads that you add on to the system. Okay, but still, because of the way the processes are written, okay, you can see that they are still a lot more efficient in meeting real-time requirements as compared to the approach that we have been using all the while, which is the loop and the interrupts. Okay, now just now you mentioned about this thing called state. Okay, so when I create a process, that process during its lifetime can go through many different states. Okay, so first time is new, then ready, then you have running, block, and exit. Okay, so let's look at what are all these states and have some rough idea of how they are actually going to be used. Okay, so let's go to the next slide where everything is filled up so I can explain. Now when I first create a thread, okay, so this is the first step. When I first create a thread or a task, okay, I will get emitted into the ready state. Okay, so when you say that a process is ready, that means it is in a sense waiting for the CPU to give it its chance, okay, to execute. Okay, that is what you mean by ready. Okay, and by general, and in general, anytime you create a new process, it will automatically get admitted into the ready state. Okay, and there can be many tasks that are in the ready state at the same time. Okay, so there are many tasks. So you can have task 1, task 2, task 3. Okay, so you can have many tasks, okay, that are all in the ready states. And out of all of these tasks, only one of them, okay, only one of them can be selected to go to the running state. Okay, so it could be task 1, it could be task 2, it could be task 3. Okay, and the person who makes this decision is this manager in the kernel known as the scheduler. Okay, so the scheduler is uh, you can think of this scheduler as the manager who looks at all these tasks, okay, and then makes a decision on who gets to run. Okay, and generally this decision, okay, is based on priority. Okay, so that is where the real time aspect comes in. Okay, so when I assign a task to have high priority, that means even though there are other people in the queue, I will get a chance to go first, okay, because my priority is the highest. Okay, so the scheduler will make a decision based on priority. Okay, so that is one of the key elements of a RTOS, a real-time operating system. Okay, the priority comes in. Okay, and now when I am running, okay, so when let's assume that task 2 has the highest priority. Okay, if task 2 has the highest priority and is running, what can happen? Okay, there's two things that can happen. It can go to a timeout. Okay, so this could be a situation where the sort of scheduling mechanism is maybe a round robin mechanism. Okay, where I say that once I'm running, after 5 milliseconds or 10 milliseconds, I will voluntarily give up the CPU and let somebody else run. Okay, so that is a possibility. Okay, where another task, okay, of equal priority can run. Okay, or it could be that I voluntarily give up the CPU. Okay, then the scheduler will look at the next available task, okay, to schedule to run. Okay, but another situation that can happen is I can go to what is known as a block state. Okay, so a block state means I was running, okay, and then at some point of time I try to request for some resource and that request cannot be met. So this is important. The difference between ready and block means ready means I still have everything, but I chose to give up the CPU. But in blocked, I actually am lacking something. Okay, I wanted something and I was not able to get it. So I'm going to go to a block state. When I go to a block state, I am waiting for some resource to be available. And when that resource is available, then I will transition back to ready. So this is also another important thing. Okay, you will never go from blocked to running. You will never go there. Okay, you will from blocked, you will only go to ready, and again it comes back to the scheduler. Okay, the scheduler's responsibility to select the next task or next process to go to the run state. Okay, so this is very important. So you need to understand this transitioning very well. Okay, then only you are able to appreciate how the multi-threaded program can run. Okay, and of course the last step is the release. Okay, where if you release the resource, you go to exit. That means you sort of terminate the whole process. But like I mentioned earlier, generally our embedded systems, operating systems, or RTOS are generally written not to terminate. Okay, they will run indefinitely. Okay, which we will see in the labs. Okay, so the process state, okay, is actually recorded in the process control block. Okay, so if you look back at the earlier slide on the process control block, one of the items is the state. Okay, and it actually keeps a update of the state, okay, continuously while it is running. Okay, and the scheduler will look at all of this information, the state information plus the priority information. Okay, and of course whether and then based on those information be able to make a decision on which task will be allocated the CPU next. Okay. uh, so in our RTX we maintain a queue-like structure, okay, to sort of keep track of which process is going to be scheduled next. Okay. Now, of course, there are other possible models mentioned here, but we are not going to worry about that. Okay. So because we are not going into the details of how the OS is implemented, but we want to understand how a multi-threaded program works. Okay. So again, this is some definitions of the states. Okay. Not to be worried about all this. We will explore these in more detail in the lab exercises so that you actually understand what are all the different states and how they actually are used by the scheduler to make a decision. Okay. So in the next set of slides, we'll be looking in more detail on scheduling, okay, to better understand how a scheduler actually makes these decisions. And of course, I will also be releasing a video on the tutorials and the labs. Okay, so look out for those. Okay, to get you prepared and ready. Okay, to enter the world of RTOS. Okay, thank you.